Okay, so here we are going to discuss the capacitance of a wedge-shaped capacitor. Okay, so it is a particular problem which is actually present in our competitive exam zone. So we have to deal with this and we have to find a way to get the capacitor when the two plates are not parallel. One plate is slightly tilted above and making it is making an angle theta with the horizontal line. Okay. So, and theta is very, very small. Fantastic. So, initial separation is given as d between the plates and is gradually increasing and increasing. Okay. And we have to find the total capacitance of this particular capacitor. So, it is already given in the question. One condition is already given in the question. That is that theta is very, very small in the sense that theta is less than pi by 6 or very, very less than pi by 6. Good. So, what are the particular characteristics of the capacitor which are actually given? So, first is the length of the plate is given, that is L. Breadth of the plate is given as B. Both plates are the same length and breadth. So, the area of the both plates is same. That is area is simple L into B. That is the area A. So to get the capacitance of this particular capacitor, we have to take a mechanism, and that is a general mechanism is I have taken this direction as the x-axis, and from this left end, I move to x distance here, take a small strip of thickness dx, which is so. So I think everybody now is understanding what I'm going to do is find the first capacitance of the particular this um small capacitor having thickness, so having particular small area, this particular small area, and the separation is given by this line. So suppose this separation is given by y, okay, and then I will integrate that. Okay, so this is our technique. So first I'm taking a small strip of length dx and breadth is similar, that is b. The area becomes a simple b dx and the separation is y. So for the small portion of the big capacitor is giving the capacitance is epsilon b dx, that is epsilon a by d, so epsilon b dx by y. Okay. So here we are assuming that since the dx is very, very small, infinitesimally small, then we are treating this particular small capacitor as a parallel plate capacitor. That's why I'm using, or I have used parallel plate capacitor formula for a particular strip. Okay. So now we are going to integrate that. But there is a two variable here, y and x, because y is varying continuously with the theta. Gradually it is increasing along x direction. So we have to convert the one variable into another so that we can the integrate all the things properly. So the method is, so I'm going to draw this picture again slightly more 1D, more 2D, to show you the relation between x and y. So this is y say, this is x. This initial separation is d between the plates, and I have just joined a horizontal line from the left end to this particular y, this particular length y, and that means I am dropping the normal on the line y. Okay, and that means this part is already d, and this part is unknown, so this is L say. This is theta. So from the small triangle A, B, and C, we can easily see that the AB part, AB by BC, is tan theta. Okay, and AB becomes, that is L, AB is L, and it becomes BC tan theta. But BC is same as the x because of the rectangular property. So that is x tan theta. Okay. So we have found the y now. Y is, so this part is already d. So y is d plus L. Okay. And L is x tan theta. So it becomes d plus x tan theta. Good. So we have found y. And we have related the y. We have found the y as a function of x. Actually, that is our aim to get, because otherwise we cannot integrate this particular uh, small expression so of the capacitance. So let us going to now integrate. So dc is epsilon b dx and y is d plus x tan theta. And since theta is constant, it is not varying, but the x and y were varying. That's why I have converted y, or I have written y in terms of x in the geometry. So now we are going to integrate. So epsilon b is constant already. I am taking those outside of the integration. It is not taking part. So it is x tan theta. Fantastic. And now, and if you see the picture, so the picture is telling that we have to integrate x from 0 to the length of the plates. So that is integration limit is 0 to L. This integration is very, very easy. Okay. So that is epsilon b. I am taking tan theta common from the denominator. It does not hamper the calculation because theta cannot be 0. Because by the definition from the starting, that is by the definition of the OH7 capacitor, theta cannot be 0. Okay. So dx becomes, so it becomes x plus d by tan theta. So this integration is giving me, that is, we know the well-known result, that is ln x plus d by tan theta, right? So upper limit is L, lower limit is 0. So if I now going to put it, and using the fact that log A minus log B is log A by B, so I'm going to first put the upper limit. So that is ln L plus d by tan theta, right? Minus ln, I'm putting 0 at the place of x, so it becomes ln d by tan theta. Good. So the capacitance becomes finally epsilon b by tan theta here. So it becomes ln L plus d tan theta by d tan theta, dy tan theta. So now I'm going to just more simplifications. I'm moving to the more simplifications. So it becomes ln 1 plus L tan theta by d. So this is the final expression of the capacitance. What we have already, what we want to get. Okay. But again, we need more simplification. Generally, it is asked to find a particular result in JE or other competitive exams. So again, I have to draw this so that I can show what I am doing for the final approximations. So this is L. So this is the theta. So this is L. So this is obviously L tan theta, right? Okay. And this is actually the breadth of the plate is B. So L tan theta, since the theta is very, very small, this L tan theta, this length is very, very small. Okay. And since the L length, it is very, very obvious from this picture. So L tan theta is very, very small with respect to B. So this particular numerator is very, very smaller than the denominator. So if I write the L tan theta by D at some quantity, say Z, say, then ln 1 plus Z can be expanded in terms of the uh, series, in terms of a Taylor series, say. So it is like Z minus Z square by 2 and further, and that is going on. The other terms are not taken into consideration because since the Z is very, very less than it is since L tan theta is greater is less than D, this particular fraction is less than 1, right? And if I taking the higher power of the Z continuously of a quantity which is less than 1, it is getting more and more smaller. So Z squared is more smaller than the Z, and Z cube is more and more smaller than the Z, or smaller than the Z square. So other terms are neglected because other terms containing the higher power of Z are neglected. Okay, because Z is less than 1. So I'm keeping the terms up to Z square. Okay. So now, and Z we have taken L tan theta by D. So the final expression, so I'm going to write this C as C is epsilon B by tan theta Z minus Z square by 2. But Z is L tan theta by D, so I'm going to write explicitly that is L tan theta by D, yes, and taking L tan square theta by 2D. So what I'm going to now, I'm going to bring the tan theta, 1 by tan theta, which is actually placed outside in the bracket, and keeping L common, so that is L square must be. So I'm taking L common outside first. So tan theta also, without, I'm not bringing the tan theta inside. Instead, I'm taking the tan theta from uh, outside from the bracketed terms. Okay, one tan theta can be taken common. Even I am taking D also, so it should be D square. So D outside. So it becomes, the first term becomes 1. Second term becomes L tan theta by 2D. So tan theta cancel out. And BL becomes the area of the plate. So epsilon A by D, we have found the term. And since the tan theta, so tan theta is very, very small, in the sense it is less than the pi by 6, then I can write the tan theta as a theta. It is a well-known approximation. But before writing that, I have to first write this. Then I am keeping the approximation right now. I'm taking this approximation. So that is L theta by 2. So this is the final equation of the Wedge-Shaped capacitor. So it is easily visible that um, this Wedge-Shaped capacitor, it is easily visible when the theta becomes 0, it becomes parallel. So this term will be gone. The second term will be gone, right? Because the theta is taken to be 0 here. So it is the first term survives, which is epsilon A by D, which is actually the uh, capacitance of the parallel capacitor. So it is matching with our result, right? Unknown result. Okay. So this is the final expression of the capacitance of a wedge-shaped capacitor, which is generally asked in the competitive exams. And here I have taken this approximation that the tan theta can be written as approximately theta when theta is less than pi by 6, or very theta is less than, yes, much more less than p pi by 6. This is very, very important. So without this particular approximation, I have to stop here. We have to stop here, and it does not hamper the physics also because again the theta is zero, giving me the tan theta equal to zero, and gives the parallel plate the formula of the parallel plate capacitor which is coming from the first term. So we are now we have checked all the steps properly, and that is all. Thank you.